Now after you knew how to find the eigenvalues, the next thing that you need to know is how to find the basis for the eigenspace. So the eigenvalues and the eigenvectors are associated together. So you have the lambda I minus a multiplied with the vector x equals to 0. So this is the equation that you are going to use for the finding of eigenvectors. So the non-zero vectors in the null space of the matrix is known as the eigenspace, or the basis for the eigenspace. So lambda I minus a is the eigenvectors. So for example, you have a matrix A here. So you're going to use the determinant of lambda I minus a equals to 0. So this is the characteristic equations that we have learned in the previous lesson, which you use it to find the eigenvalues. So in this case, we found out that the eigenvalues are 3 and negative 1. And there are two eigenspaces of A, one corresponding to each of these eigenvalues. So let's assume that your x vector is x1 and x2, and then you're going to use the equations represented by the green colored lambda I minus a multiplied with x equals to 0. So you're going to put them into the matrix form. And now since we found the eigenvalues, we just need to substitute the eigenvalues value into these equations. So you replace the lambda with 3 for the first case. So if lambda equals to 3, and your system of linear equation will be simplified into this form. So the last one will be here, 1 and negative half and 0 for the first row. So we know that the general solution for this case will be x2, since it doesn't have a free variable. So we know that x2 is a free variable, is t, and x1 can be expressed in the form of half over t, and you put them into the vector x and factorize out the t. So this will be the basis for your case. And the second case is when you substitute the value of the lambda equals to -1, the second eigenvalues, and you're going to reduce everything to the last form. And then since x2 doesn't have leading one, so x2 will be the free variable, and x1 we have a leading one, so it will be expressed either in the form of x2 or you can directly get the values. And then you are going to put it into the vector x here, and this will be your basis. So we have found two bases, each corresponding to one of the eigenvalues, and the eigenspace for this system will be 2. Now let's consider another example here. Find the basis for the eigenspaces of matrix A here. So using the characteristic equations, determinant of lambda I minus a equals to 0, so we are going to find out what would be the value of lambda. So in this case, we only have two values for lambda. And when we substitute the value of lambda equals to 2 into the equations, so I skip the step on the calculation. So why don't you try it out on yourself? So you try to use this formula again, and then you substitute the value of the lambda to get the basis. So the answer for the basis when lambda is 2, we have 2 here. So -1, 0, 1, and 0, 1, 0. So these are the non-zero vectors that form the basis for the eigenspace. And we have another eigenvalues here, lambda equals to 1. So you substitute into the equations and then you solve it, you'll get another basis. Now move on to the powers of a matrix. So let's imagine that you have a x raised to the power a matrix A square multiplied with a vector x. So you can express this in this form, a multiplied with ax, and we know that if ax has an eigenvalue, so it could be expressed in the form of lambda x. So you take the lambda out because it is a scalar, you can simply move it out, and you have the lambda multiplied with ax. And if ax has an eigenvalue, so you can express this in this form, and eventually you have the lambda squared x. So this means when you found the eigenvalues for the original matrix A, so when you have another matrix which is the, let's say, a raised to the power of 7, so this should be a new matrix B where it is a raised to the power of 7, and the eigenvalues associated with this new matrix B will be the corresponding eigenvalues of the original matrix A raised to the power of 7 as well, and the eigenvalues corresponding to B will be raised to the power of 7. So this is just a proving for the eigenvalues and invertibility. A square matrix A is invertible if and only if lambda equals to 0 is not an eigenvalue of A. So why? Let's look at this condition. So the determinant of lambda I minus A equals to 0. So this is the characteristic equations that we use to solve for the eigenvalues. And you could actually find out that the lambda could be expressed in the form of a polynomial equation. So maybe lambda square plus 2 lambda plus 1 or something like this. So because this must be equal to 0, right? So we have a 0 here. Now let's look at this case. If the constant here is 0, so most probably you'll end up with something like this. So let's imagine your original equation is lambda 2 minus 2 lambda plus a kn equals to 0. So if this kn is 0, so you can factorize out the lambda here, and lambda equals to 0 is a solution. So when you have a lambda equals to 0, when you substitute back the lambda value into these characteristic equations, you actually end up with determinant of minus a. So you can factorize out the minus, and then you get determinant of a is 0. So it is a non-invertible, which means that it is no solutions. And if the kn here is not a 0, so lambda equals to 0 is not a solution, which means that determinant of lambda I minus a equals to 0, you will be able to find out a value for lambda which is not equal to 0, and which prove that